So then, welcome back from the coffee break, and welcome to all who joined our online meeting, our online stream. I'm Claudius, and it's my pleasure now to announce our first keynote talk given by Natalia Ares, who is a professor in the materials department at the University of Oxford since 2013. There, she works on experiments to advance quantum technology with a focus on artificial intelligence for quantum device control and quantum thermodynamics. Today, she will talk about machine learning-based control for quantum devices. With this, Natalia, please go ahead.
Thank you very much. And, I'm really sorry that I cannot join you in person today. I know I'm missing a lot, but I'm really glad that I can still present today, and I want to thank the organizers for that. So, okay, let me tell you all about machine learning-based control of quantum devices. There have been some absolutely fabulous, staggering, really, breakthroughs in machine learning and in quantum technologies. And the natural question is, well, what can machine learning do for quantum technologies, and what quantum technologies can do for machine learning? So this talk is not about what quantum technologies can do for machine learning, but what can machine learning do for us? So in the development of these devices and complex quantum architectures, where can these new techniques and approaches in machine learning can help us? And I'll tell you how we went about it. So in principle, you know this very well. Some of you have been there. We are in the lab, we check signals, we make decisions, we fix parameters, we check the signal that comes out of our fridge, and we make decisions. And either at low temperatures or not, this is something that happens in ion traps, in semiconductor chips, in superconducting chips. And there are many ways to actually go about it and have a protocol of how to calibrate, tune, and make decisions about the parameters as we operate these devices. For example, there are for superconducting technologies, there are these directed cyclic graphs that one can use. And they go from very basic tune-up to very careful tune-up. And that's exactly where machine learning can help us in navigating these tuning and characterization protocols. And I hope that today I will give you, I convince you that actually this is a very powerful tool that we really need. So indeed, as I was saying, from the quantum chip, as you cool it down or you prepare it for operation, there are many steps before we can actually operate these devices as a qubit. And then once we have a qubit up and running, there is a long process as well of optimization that sometimes we do it, sometimes we don't, but it's certainly possible. Now, this is a very tedious and time-consuming process performed typically by us, but by humans. And the problem with this is that it is a big parameter space, even when we are dealing with a limited number of qubits. Also, one can say, well, why don't you just write a script and plan what you're going to do and just run it? Well, this is not actually possible, and the reason is that there is big variability between devices. Devices are slightly different because of fabrication defects, because of material defects, and there is a reason why quantum devices are good sensors. So we just need to adapt to those differences, and that's what we do as humans. We have certain expertise of how devices that look alike work, and therefore we apply that expertise to overcome that variability. Also, we have to get it right most of the times, so we don't have much room for errors, and this makes this process, well, as I said before, difficult, but completely impossible, really, if you want to scale up this approach to billions of devices. So now what we have done so far in my group was to focus on completely automating this process using machine learning. And this is also not a very easy task, and the reason is that, well, data sets are small. We don't have a lot of this data. It is expensive to acquire. Again, devices are different, so if you're going to have a machine learning approach, it has to be robust. For many devices, there is no use of an algorithm that can tune a single device and that's it, right? Also, we have the problem that there are very flat optimization landscapes. So our qubit typically works in a very narrow parameter space, and it's surrounded by non-working parameter conditions. So this doesn't help optimization in SHRAN, and that's why many times simple optimization fails. Now, we also have noisy data, in some cases hysteretic data, but all these can be overcome. So these are the difficulties. But I can tell you a bit about the progress we've made in taking a semiconductor chip and operating it as a qubit. And I would focus on semiconductor chips today. But please bear in mind that some of this technique is, and this is something we are working on, can be taken to other qubit realizations. So the first question that we pose ourselves is, are device measurements, what are the device measurements that humans require, and are those the same measurements that machines will require? So, well, for example, in a semiconductor chip, we might have a very super coarse tuning, and that's what we do. Once we have a device in the fridge, we basically do very rough measurements of, in our case, current or some other quantity as a function of two parameters, in our case, gate voltages. And then we go to more kind of fine or coarser tuning and characterization, followed by fine tuning. And finally, we are basically zooming in and in the parameter space. And finally, we might want to change entirely the space of optimization to optimize qubit operations. So, for example, we might have current as a function of frequency or time. So the question is, again, are all these steps necessary, and how we would go about automating all this process? So there is a lot of work, especially in semiconductors, using machine learning for identifying particular transitions. So this is a non-exhaustive really list of things that have been done. But today I'll focus on our ambitions and our path towards this goal. And the reason is that we have to think on really scaling. And this is, for example, a sample from Ferdinand Kumets at the Niels Bohr Institute. And you can see now that all of those of you who have spent some of your time tuning maybe 1, 2, 3 quantum dots in semiconductors, you can clearly imagine how tuning these would result, at least manually. So where are we in this path? Well, so we have several pieces of work that go from again very beginning of the tuning procedure to trying to define and operate a qubit. You would see that as there is a natural progression from non-deep learning approaches in machine learning to more deep learning type of work. And the reason is because when we introduce, we have a new device, we have a huge parameter space, and this is something I'll show you now. But then we want to as we home in smaller and smaller regions of parameter space, we have more availability of data, and that means that deep learning techniques become a lot more useful. But when there is no data, we have to go with some other approaches, and these are different types of machine learning approaches that are designed to work when data is scarce. So I'm not going to show you everything today, all of this work today, but I have chosen some, and I would go super fast over this, but this is just to give you an overall idea. And if you are interested in one of these particular topics, we can talk a lot more about it. So let's maybe focus on tuning. And here we took, again, an approach which makes use of the fact that, makes use of the fact that not a lot of data is necessary. We just don't have that data. So, okay, we have a device, and in our case, our devices work really, you can think of them as transistors. So we have a bias voltage, and they are controlled by gate voltages, and there is a current that flows through that circuit. So when we first have a device, we might want to measure current as a function of 1 or 2 gate voltages. And what we see is that this transistor is most of the times on. For most of the gate voltages is on, this red region here. And for some of these are completely off. This is not interesting at all. What we want is that middle ground where the transistor shows quantum effects. So you can see here in the transition between current and no current that we see some features. And these features are those that we are looking for when we first find a device. But as you can see, okay, this is just a cut for gate voltage 1 and 2. If we were to have 3 gate voltages and have more control of this device, then suddenly now we can define a surface that separates regions of current and regions of no current. And this is a model of such a surface here in 3D. And this is a measurement that we perform on such a surface, what we call the hypersurface. It took us a long time to take this measurement. Actually, it took us we did it over Christmas, and it took us, weeks of just measuring and measuring and measuring current as a function of a voltage. Nobody would ever do that, trying to focus really on the tuning of these devices. We did it because we wanted to show, and we wanted to understand ourselves how the tuning problem looks like if we don't restrict ourselves to 2 dimensions, because machine learning algorithms have no need to restrict themselves to 2 dimensions. So we thought, well, can we present an algorithm that not only works in 3D, but actually works in a multi-dimensional space of many gate voltages and presents a given hypersurface? And can we find in that hypersurface regions that are good for tuning? So, well, the answer is that yes, one can do that, and with little data, because of course we cannot take this data in 8 dimensions, right? So already 3 dimensions took us long enough. So what does this algorithm do? Well, it starts by having some idea, some model of this surface, which makes basically no assumptions. But in order to build the most minimalistic model, we need some initial information, some initial observations. So we do that in real time. So the algorithm asks for some current measurements to the device, and well, these initial observations are used in a Gaussian process to build a model of this surface. And once we have a model, okay, we can, by performing more and more of these initial observations, and that model gets better at fitting those points, we can choose some promising locations to investigate further. Okay, we know more or less where this hypersurface might be. let's look in the surroundings of this for features that indicate that it's a potentially good looking place to start tuning our device further. So we can investigate these locations in real time and then feed that information back to the model. And in that way, we can get our model better. And the next location we are going to find, it's even better in principle, because it's in the light of the information we recovered before. So this is the algorithm in rough terms. Let me show you how it works in step by step. So first, you can see here I plotted this in 2D so that it's easier to understand. But you have again a pink region with current and a blue region without current. And what the algorithm is going to do in the beginning, it just has no information, it would explore. So it would start ramping the gate voltages in a random direction and would measure the current as a function of this direction in which the gate voltage is ramped. And when the current drops below a certain threshold, it would stop, and it would make a note of that point as belonging to the hypersurface. But once it's there, it will make a little trace just around in the limit of that hypersurface, and it would check how the current looks as a function of the gate voltage. If it looks flat, then that's not interesting. If there are features, then that's interesting. So here you can see that we have two pieces of very important information. One of it is, well, what is the limit between the pink and the blue, which the algorithm doesn't know. You see it now, but the algorithm doesn't know it. So it's starting to build a model of where that hypersurface might lie. And also, you can see here that there is this model line and the observations as points. But you also see that there are different tones of yellow and green. Green are uninteresting regions, and yellow are interesting regions because they show features. So we can build a model of where this hypersurface lies and where the basically where the features might lie in this device. And with this information, the algorithm will then choose a very promising point in this hypersurface and would investigate it further. Because now, okay, we now know more or less where this hypersurface is, so we can spend more time making measurements because we have some guess that they are going to be good. So we investigate here, we can do a 2D plot, a 2D cut of this hypersurface in the surroundings of that hypersurface. And if we find the features that we are looking for example, these small triangles that indicate that we have a double quantum dot device, then okay, then this is seen as good and is fed back to the model. So now let me go into detail in two small things in this model. The model is a Gaussian process. What we have is we have the real hypersurface, which you can think now in 1D. We go down in dimensions just to explain this, but the real hypersurface is a function we don't know. And the prediction is the green line that you can see here. And as we take different measurements, what happens is that our real hypersurface starts looking similar, our prediction starts looking similar to the real hypersurface with some uncertainty. And these models allow you to calculate that uncertainty. So this is the way that we basically use these Gaussian processes. And also you can think that it's not easy to choose a random in the hypersurface when we want to choose a random point, and I can tell you why we would want to do that. But in principle, because it's difficult to have a random distribution of the points of the hypersurface, what we did was to simulate Brownian particles in the volume defined by the model hypersurface. And in this way, every time a particle hits this model hypersurface, then that's a pretty random or apparently homogeneous distribution of points in that hypersurface. So these are just details, and well, I told you why would we want, if we have a model, why would we want to go to a completely different point randomly generated? Okay, well, the reason is that it's a problem that in machine learning is identified as the multi-armed bandit problem. So the objective, imagine we have somebody that is gambling, and the objective is, as always, maximize the reward. So the question is, which machine should this player play next? Because there is some machines that have a quite high success rate. So one could think on just exploiting that knowledge. But there are some machines that haven't been yet tested, and therefore they might be even better or might be worse. And that's the exploration part. One might want to explore this new machine. So one has to basically balance this exploration versus exploitation trade-off. And this is part of our machine learning algorithm in finding the locations that are interesting to explore in this hypersurface model. So just to give you an idea how it works, this we tried in a laterally defined double quantum dot in gallium arsenide to start with. And I want to show you that it doesn't limit to that at all. And this one had 8 gate voltages. And so now you can imagine this hypersurface we've been talking about is now, living in 8 dimensions. And what we have done is just randomly, and as I told you, it's really not easy to go randomly, but you can go randomly and try to find what is the average number of successes you have as a function of time you spend exploring this space. And okay, you can see that if we go random, really, it takes quite a long time to see something that looks like a success. Now, this is the average number of successes, so you can imagine why. Well, really is that, you can say, oh yes, this looks like we have tuned the device and it's looking good, but that opinion changes from person to person. So what we have done is just ask 3 different people, 3 different labelers. I think one of them, it must be sitting there, Florian. And, we gave an average number to that success as an average of these 3 different labelers. And, well, you can still see that in random is very low. And in our algorithm, you can see that we achieve a lot better performance for different runs that are the different colors that you can see. Now, of course, the labelers didn't know which were random and which were our algorithm, of course. and that's a good check. So what we've seen is that the random takes more than 9 hours. Human experts, we asked around, and we got a round of 3 hours. The most confident ones, maybe 2 hours. That's more or less the range. Our algorithm can do it in less than 70 minutes. You would see that we have improved on that quite a lot. But actually, does it completely automatically, which is the important part. One doesn't have to sit there. You can play with this. There is a simulation demo in our GitHub repository, and I encourage you to play with it. It's quite fun. So also, this knowledge of the hypersurface is giving us a lot of more information than we think, because if we have the one hypersurface from one device and one model hypersurface for another device, we can basically find the transformation that takes one device into the other, and therefore have a quantitative measure of device variability. And this is what we done. So you can see here that actually the matrix that maps one hypersurface into the other for different devices shows that they really don't look alike. And this is a problem of variability we started talking about. And that's why we cannot really automate the tuning so easily. But after a thermal cycle, this is quite interesting. What we see is that the hypersurface basically just expands and contracts, but it does so in mainly scaling its diagonal. So that was quite an interesting finding. Now also you can go further with this, because this algorithm really doesn't care which device you're talking about, and it just builds a model of this hypersurface in whatever type of architecture. So that's what we did. We did this, we ran this algorithm, similar version of it really, for different types of devices. So we have a silicon FinFET, germanium silicon coarse shell nanowire, and a silicon germanium heterostructure. And for this, we work in collaboration with the University of Basel, with Dominic Zumbel's group, and for the germanium heterostructure with IST Austria. And what you can see is that, this is just, again, just to show in 3D, but what you can see is that the hypersurfaces are completely different. Well, not completely different, but they have different shapes, right? And this is to be expected, because the coupling of the different gates is it's different in different devices, and some of these work in accumulation and some work in depletion, and well, in this case they are all holes, but they could be electrons, as in the gallium arsenide case. So what we can see is that the average number of successes, again, as a function of time for the FinFET, nanowire, and heterostructure changes. For the silicon germanium heterostructure, we had something like 90 minutes in average, the silicon FinFET something like 30 minutes in average, and the germanium silicon nanowire 10 minutes. And you can see that as the dimensionality drops, the tuning times, of course, drop. So we have shown that we can actually tune automatically. This very super coarse, as we call it, tuning can be done fully automatically, and in a way that it works across different semiconductor structures. So actually, something that we are now looking into is that, okay, until now we had given our machine learning algorithm zero information about the theory of these devices. It's just a black box. We are trying to build a model really fitting, really using these Gaussian processes without information of anything really. It's a bit of a black box. So the question is, well, shall we introduce some knowledge about the device? And of course, there is a trade-off, right? Because if you introduce information about the device, then of course it cannot work across architecture so easily. You would have to modify that physics model. But of course, with a lot more information, you can tune a lot faster. So let me give you an example of this that we have been working on. So what we have done here was to calculate the electrostatic potential for a given gallium arsenide device, laterally defined in gallium arsenide. And okay, you can, calculate the electrostatics of the gates at given gate voltages, and you would see something of this sort. Now, you can also calculate the disorder potential that might be lying in the background. And this disorder potential, of course, we have no way to access, right? We know it's there. We know it affects our transport. We don't really know exactly what it does. Well, how it looks like, let's say, and how particularly it affects our transport. So, okay, but we can guess. We can make a guess of how this disorder potential might be. It might be completely wrong. But okay, this is the thing. If you have the electrostatic physics model of the electrostatic potential plus the disorder potential, you can try and see if you can calculate the electron density and see if there is a path from the electron reservoirs here and there through maybe an isolated region, our quantum dot. So as you can see here is the potential energy. You can see here that indeed we seem to have a single dot here between source and drain. And okay, but this is already telling us something. It is telling us that if this disorder potential is right, then at these given gate voltages, we should find single dots, right? In principle. That might be completely wrong, but that's something that we can measure and we can inform our model. So that's exactly what we've done. By fitting different disorder potentials and seeing what the electrostatics lets us to, we can find really, we can make a really good guess of our disorder potential that it's based on our transport measurements. So here you can see how, in fact, we can find different double dot configurations that we have found just guessing this disorder potential, just inferring it using Bayesian inference. So actually, so we did this doing, of course, to compare it, we compare the Bayesian inference of these disorder potentials with some random disorders that we might create. And of course, the posterior samples of this Bayesian inference are right 67% of the time, which is not perfect, but still bigger than these random disorders that are 28%. So one can run this algorithm, still we have a better and better idea of the disorder potential. And actually, you can, again, calculate and think how this disorder potential might look like for different thermal cycles and for different devices. Here you can see this is the inferred disorder potentials for different thermal cycles of the same device. You can see that now there are points instead of the whole picture of the disorder potential, and this is because you need to computationally compromise and reduce the number of, in order to reduce the number of parameters in the model. So you can see that indeed the disorder drifts a bit during, changes a bit during thermal cycles. But this is really something that is great because it's allowing us to infer things about a completely hidden variable of our device, which are the disorder potential. And this is information we can feed back to our fab to give a qualitative really measure of the quality and the variability of our devices. So, okay, that's all about tuning, and I'll go a bit faster from now on into more steps of characterization. Okay, now we have some idea of how we get more or less the device to behave as a double dot, going blindly on the physics or really introducing some model to it. But also now when we are close, we still need to characterize and measure. One of the techniques we have used is deep reinforcement learning. This deep reinforcement learning is great for games because the idea is that there is an agent that can perform certain actions, and certain actions have some rewards. And the agent would go trying to maximize these rewards with certain constraints, making a strategy really to maximize the reward. So for example, once we are more or less in the regime we want in terms of, for example, forming double quantum dots, we have maybe this current as a function of gate voltage, and this takes a long time really to explore. So one of the things that you can do is divide this parameter space in blocks and make an agent find its reward, which is a particular feature in this stability diagram, in this current map. So you can find, for example, these islands of current, these bias triangles I talked about. So indeed, this can be, we are now instead of current, you can do it with very other techniques for very fast acquisition. For example, in We have done this with the UHF-LI high frequency lock-in amplifier, and okay, then now this is very important, because now you have to balance how much time your machine learning takes to make decisions and how fast your acquisition is. So in principle, you can perform some initial observations in real time. And what we do here, once the agent is in a given block, is classify if this block is worth measuring or not, spending time on or not. And then the reinforcement learning agent will make a decision if to go up, down, to the sides, or in diagonal. It would perform the next measurement. And again, it will classify and feed the DRL agent with a decision. So this is in broad terms. Let's go a bit more to the detail. So what we do is we initialize the algorithm with a certain current as a function of gate voltage. This is just to give us an idea of what are the highest and the lowest current values that we are going to measure. Then the agent starts in a random block, and it performs just random pixels. It measures just random pixels. So it can create a state vector, let's say a vector that has the mean current and the standard deviation for different subblocks of this block. Now, this state vector can be now pre-classified. So if there is something interesting, like features of some kind, then that's great. If it doesn't, then we should immediately feed that state vector to a neural network that would tell us if we should go up, down, in one gate voltage, in the other, or in a combination. So this is what our neural network does. It gets some state vectors, let's say some idea of the mean and standard deviation current, and gives you as an output what you have to do in terms of getting what you want, getting a reward. So if this pre-classification actually finds something interesting, it would do a better measurement, a high-res measurement, and it would classify it again. And if it's what you're looking for, like bias triangles, it would terminate. If not, it would go back to the deep reinforcement learning agent. So indeed, it doesn't matter where you start. So this in blue is where you start, and in red is where you end. You always will, the number of blocks that you would measure with this deep reinforcement learning agent would be always less than if you go with a random decision agent. So this decision agent still looks at it still classifies if it's useful or not, but it just takes the decision of moving in different directions randomly. And still, as you can see, it performs worse than the DRL agent. Okay, so now we're homing in parameter space, in a small region of parameter space and bias triangles. But that's not the end of the story, because this is how it should look like, and this is how it looks like. And if I ask you to tell me now, well, how can you define the difference between those two? How can you tell an algorithm how do these two differ? You can tell me, well, okay, one is sharp, the other isn't. And then this is like a bit blob, but maybe also, but you know, I want to change it, but not in a way that the current is lost completely, or so it's difficult to define in parameterize this problem. So it's tricky to make an algorithm to actually fix this, but we could do that and actually find an algorithm that can take us the closest our device can make it to this idealized version of how it looks like, and definitely that has more probabilities to lead to a better qubit realization. So here you go from this blob to the really distinguished two bias triangles. And how do we do in order to not parameterize this problem, because it's tricky? Well, we perform a real an initial scan, and we give a score, and you will see how we score this without having to parameterize. We choose some gate voltages then to change to change these bias triangles, and we perform another scan and see if the score has improved. So basically, the problem is to give this score, because how do we score it? How do we say, well, this is good and this is not good? So what we do actually is we use a neural network to encode this image, this measurement, into a latent vector space. This is basically extracting some high-level representation of this figure. And this is actually multidimensional, but here I'm showing you a particular representation of this multidimensional latent space. And something that you can force into this is how far, let's say, how these different characteristics of this image organize in this latent vector space. So you can try to reinforce the fact that, for example, brightness is in one axis and sharpness is in other. Of course, you don't want to do that because by hand, because we cannot really put this into particular boxes. But something you can do is to say, well, I have a target. I like to see something like this, not exactly like that, but with some higher level representation, something that looks like this. So then what the algorithm would do would be, once it places this new figure, this new picture or measurement in the latent space, measure how far it is from the latent space. Because if it's close, it means that it can share, or it can be close in a high level representation. So they have something in common. And if they are far away, they don't. So indeed, this is more what I'm looking for rather than this. And this is something that you can put into a score. And you can use that score to then change the gate voltages, and these gate voltages can come back. And then you can come back and repeat this process. So indeed, you can then, do some kind of optimization. I will go quickly through this because actually this is very simple optimization of the gate voltages until you home in into a set of gate voltages that, in this case, minimize the score. It can be maximized in the score. In this case, you want to maximize the score and you minimize the score, and you can see that it does so quite quickly in terms of the number of iterations. And you can see how in different runs these bias triangles change in gate voltage space. So indeed, this algorithm helps us to do the fine tuning. And finally, you want to operate this into, you want to find places to operate your qubit and find the optimal. So one of our latest works have to do with basically detecting a feature that it's very important because it allows for readout and initialization in many of spin qubit realizations, and that's Pauli spin blockade. Just to make it easy and not go through this, basically one way of looking into Pauli spin blockade and seeing if the spin is actually a good quantum number of which you can make a qubit. Basically, you can measure the current with a certain bias and with the opposite bias. And what should happen is some of the current in your bias triangles should disappear. So you can see here that there is a region where this current is suppressed. Well, then, we have a Pauli spin blockade and we are happy. And this is a particular FinFET device that I'm showing you here. Now, the thing is that you don't know which bias triangle is going to show this. Sometimes you can, but it's not always. The reason is that there are effects like spin-orbit coupling that can make this identification not straightforward, or because there is you cannot count exactly how many charges you have in your quantum dot, and therefore it's not trivial. So there are many effects that can mess this up, and you can easily spend months looking for Pauli spin blockade. So we indeed can do this using classification. This is hard to do, obviously, because there's not a lot of Pauli spin blockade data, because it's so hard to find it. And so as a community, I think we should start, getting a bank of different bias triangles and different data, so that we can actually use deep learning for these tasks. In this case, we had some data, and we augmented it, and we combined it with a simulator, and we also cross-validated the different. We basically retrained the same classifier 10 times, made an average. All sorts of kind of go-arounds to try and deal with small number with a small number of real data. What we can see, this is our algorithms calculated with different types of data, like simulated data, experimental data, mixed data, and all these classifiers find Pauli spin blockade and say that there is no Pauli spin blockade with a 96% accuracy. So, okay, Pauli spin blockade, and there we go for more optimization of qubit operation, and this is things we are working on. Oops, okay. So, and these are, it's an effort we are doing all together, really. So, from Oxford, we, as I'm talking to you today, we also operate and control other computers connected to other sets of electronics, connected to other devices. We do this in collaboration with, we started with Dominik Summel in University of Basel, who have been really supportive in when we started this project, and really was optimistic that this was going to work, and indeed it was very, very successful there as well. So we set up these to control their experiment as well, and we currently have some collaboration as well with Andreas Führer that we are developing. We also control some of the experiments in IST Austria and in the Niels Bohr Institute, together with Fadin and Kumeth and Yorgos Katsaros. And we are setting it up as well in UNSW. And there are a bunch of companies that also have been helping me along the way. We are recently formed a consortium with DeepMind, with MindFoundry, Riverlane, GraphCore, and Oxford Ionics to develop these machine learning algorithms and use some of the things that we have been developing already for superconducting qubits and ion traps. And we have spun out a company as well separately, and we have, again, collaborative efforts with this company in the lab. So just to tell you that there are other things we do in the lab as well that are of a more fundamental nature for those interested. We have also been looking into the thermodynamics of time, but this is going to be something that becomes more and more important as well for as we will more complex quantum circuits that have to do with the quantum energetics, really, how devices dissipate, thermalize, when there are coherent quantum states involved. And with that, I'd like to thank, my group, fantastic group. It's an old picture, really, since COVID. I'd like to thank them all and all our collaborators. And, there are positions open, so join us.
Yeah. Thanks a lot, Natalia. This was a really interesting talk with a very interesting topic. I'm sure there are several questions in the audience. Do we have some questions online? No, not at the moment. So please put in some questions. I have actually one question. You answered the overall time for the optimization using the artificial intelligence, but for me it would be interesting how many cycle times you have to perform to take a measurement and optimize to get to this result finally.
Well, the thing is, it depends of measurements of which type, no? Because I mean, if it's not going to be very promising to start with the approach, then one might think, okay, I'm not going to spend much time on it. So you might measure a single trace and look that it's, it's not very, it might not be very promising, so then you don't spend time on it. If it's more promising, then you can take, a closer look, and then you will make maybe a 2D measurement or a higher resolution measurement. So in each iteration, there are different things happening. Sometimes there is just very, very little time measuring. Sometimes there is a lot of time measuring. So it's not. That's why we talk about times to get somewhere, because each iteration might change completely in terms of time. And something that, of course, here I've been showing mostly current, but you can measure, as I said before, you can measure at with a reflectometry, with a reflectometry, you can measure that faster, and therefore. Again, what you do and which decisions you make using machine learning in every step change, because you might want to spend more time calculating rather than you might want to spend more time measuring rather than calculating what you do next. So there is again this exploration versus exploitation, right? What do you this trade-off and how do you deal with it?
Oh, okay, so this renders my next question obsolete, which was about how do you decide on how much time where you spend the time budget on the calculation of the artificial intelligence algorithm or on actually the measurement of variation of the parameter. Thanks for answering this directly. So I'm looking again into the audience, and I have a question over there. Clemens, please go ahead.
Yes, thank you. Natalia, I really like the part where you looked at the disorder of the material using your methods, and I have kind of two questions for that. So one was you showed in one part you showed how the disorder changes with thermal cycles, but in an earlier part of your talk you also showed the mapping of the gate voltages to the hypersurface, and that didn't change with thermal cycling. So I was wondering what the difference between these two cases was, and if you can comment on that. And maybe a second question would be, like, could you use this method to maybe constructively learn something about the disorder, the origin of the disorder, or the dynamics of the disorder somehow?
Thank you for the question. Yes, indeed. The difference between these two things is that between why did it change? Why did it seem that it change in one case and it didn't seem to change in the other? The reason is that we are looking at the when we are looking into the matrix, we are looking into how one hypersurface maps into the other. So the hypersurface does move. So there is a change of the electrostatics in general. This can be, really charges that are trapped somewhere and homogeneously, let's say, but they move the hypersurface like in a sort of breathing mode. And the problem with when we look at the disorder in just one go is that we are basically taking a 2D cut of that, and of course. In one particular, let's say, 2D plane, it would look like the disorder is completely different. But what might have happened really is that the thing had scaled out of, and the same disorder potential just would be found, but at a slightly different region of the hyperspace. I hope it's clear what I said. This multidimensional things.
Try to rephrase your answer somehow. Like you're saying that, like just by essentially a different mapping of your gate voltages, you could recover the previous hypersurface. So essentially, you're saying it is charges. The charges are still there. They just moved.
Exactly. That's exactly what we think it's happening. And the reason and the question about, you know, can you use this? And I said, and I think absolutely. Actually, we are now finding that there are some devices in which, well, you know, you can go ahead and infer the potential all you want. It doesn't make a difference. So the electrostatics, it's really defining the problem, and it's telling you, look, the disorder potential is not that important for these particular devices. So it can really, this is really what you would like, right? To say, I like a device in which actually I can model the electrostatics and I can find the dots right away without any influence of the disorder potential. So definitely, at least we have an internal quality measure of our devices. If we see that, you know, we get the electrostatics and it can tell us right away where we are, then it means the disorder is really low. So that's something that indeed I think can be used as a variability measure.
Okay, thank you.
Thank you.
Thanks a lot. Are there other questions in the audience? Yeah, there's one. Frank Deppe, please.
Thank you for the very nice presentation. I have a rather naive question on the time performance where you compare to the human operators, essentially. The times you're giving are these, I would imagine naively that like a human operator can be very quick for one particular device, but very slow for another one. So the variance should be huge. How is this for your algorithm when you gave an average time, I guess, right? How is the variance there, for example? And as a follow-up, are there sort of specific cases where your algorithm is particularly faster than human operators, or others where it may even be slower?
Yeah, definitely. That's right. So we are always talking about average, and I'm afraid I'll have to look at the exact numbers. They are not huge in terms of variation of the numbers of these average times. But something that I can tell you is, yes, sometimes random. It's insanely fast because it's super lucky. You know, you can get super lucky. Even you know, it has happened to us that we go with random and boom, directly. But okay, you know, you cannot rely on it because next time it's gonna take. So you can see that the basically I'm not sure I have this data here, but what you can see is that the random, a bit like I did show the tail of the DRL random, no? So it has a very long tail. That's the thing, and yeah, I mean, in some sense, sometimes you can get lucky. It can be very quick, and the same with our algorithm. Sometimes is you know, it lands very close to something very good, and then suddenly, you know, it does really well. But it's more reliable, and the reason is that it's actually building information. So it's accumulating information, and therefore the spread is not as big as if you do it randomly. But certainly there are moments that it's random is a lot quicker than anything else, and that our algorithm is slower even than humans. Certainly, sometimes I think, if I remember our error bars well. But the thing is that the distribution is the tail of random and manual tuning is it's higher, I think. So in some sense, if you let it running many times, even if it's unlucky and you run it again, it will always get you there, which is something that might not be the case if with random. It can take really forever. At some point, some of our random approaches we had to stop because they after 10 hours trying to find it, it's like, okay, enough. we would stop it there, and it never found them. With humans, I guess it depends. It depends a lot on how lucky you are sometimes, how much you know about the device, and this is something it's really difficult to isolate. Because, I spent all my PhD tuning, silicon germanium devices with holes, and I'm very used to tuning these kind of devices, but I was not used to tuning gallium arsenide devices, and that's, then I'm slower at that. So it's really hard to put a human benchmark on it, but we just don't want to do it randomly, manually, and that's why we have to go through automation for sure.
Yeah, I think we all agree on that we don't want to spend PhD time on tuning up our qubits. Natalia, thanks a lot again for the contribution in the virtual way. Too bad you couldn't be here, but thanks again. Great.
Thank you. Thank you, everyone.